good evening. Hope all are safe and healthy. So, welcome to our day 2 session of machine learning and GenAI certification program. And I hope you are all enjoying the previous classes and somewhat knowledge you have got from all these things. And so, before going into our classes, I just want to read your feedbacks and just want to clarify some few things. So most of the people are commenting like we are not able to open the links and the Google links, whatever I have provided yesterday, Google Collab links, and can't able to see that content, all these things. So actually, we are providing that links in WhatsApp channel. So before while you are registering, there is a WhatsApp link is given. So you have to register in our WhatsApp group. So in that WhatsApp channel, whatever I teach here, and even PPT also I'll share there. So PPT recordings and that links, collab links, everything will be given there. Data sets and everything will be there. So you can access there itself and you can work on your your Gmail accounts. So that is one comment I got from so many people. And a few people, actually, few people are completely, different comments. Like few people are wanting me to go a little bit slow, and a few people are wanting me to go a little bit fast. Actually, I feel I am going with the medium speed because from the registrations I can see most of the people are from students. So maybe for the industrial persons, maybe you feel like a bit slow. But students actually they don't have any basic knowledge of AI and ML. So anyway, from Monday onwards, we are jumping into DL. Completely in the world of DL, we are going to see all the DL concept, deep learning concepts, and GenAI concept. There anyway, we are not going to deal any basic concepts of ML. So here itself, today itself, we'll finish all the ML concepts. So from Monday onwards, it's completely a bit fast. So up to that, I hope you'll have that knowledge of complete ML basic concepts. So from Monday onwards, I'll be a bit fast. And a few more comments I got like, you want me to use, the classes should be provided in the morning session because it's very difficult to have in the evening session. Actually, we are faculty and morning we have all our classes, regular classes, academic classes. Actually, we fix this timing because everybody are relaxed at this time and you will enjoy the sessions because everybody will maybe they'll be in their homes and peacefully you can enjoy our sessions and anyway we get our sessions up to Thursday. Friday will be a complete question and answer sessions and Saturday and Sunday you'll get to work out all these practical sessions whatever we have learned in our classes. So in that way we have planned at these timings. So please be stick to these timings and it's actually for this session it's impossible to make it on the morning. Maybe for the next FDP we will plan, definitely we will plan in the morning sessions if possible. And other reminding are I'm getting a good feedback. So I'm seeing everybody are getting we are understanding so much and thank you so much. And now we'll go to our regular session. So yesterday, at the end of our session, abruptly I stopped at the K-means algorithm because the time is not permitted. It's already 8:30 yesterday. So today I'll start with the K-means again. So K-means is a unsupervised algorithm. It is a clustering algorithm. So I already told you what is a unsupervised algorithm. So there won't be any labels. It's just grouping. So clustering algorithm K-means also what it will do, it will group the items, group the data points. But there should be some procedure to group the data points. So K-means will work on the basis of centroids. So if I have a data points of some 5, so first K-means will calculate what is the centroid of these 5 points. So depending on the centroid, the distance, Euclidean distance will be calculated for each and every point. So wherever is close, the similar distances, nearby distances are there, that will be grouped to one point. So nearby, no, that, like that, so many centroids will be created. And again with the iterations, the centroids will be changed, comparing the similarities between the points. So automatically at one point of time, after so many iterations, at one point of time, the centroids will be fixed on around the centroid, the data points will have the similar characteristics. So that data points will call it as a cluster. So there will be so many clusters, one cluster, two cluster, three cluster, like that. So it's completely based on the centroid. With the iterations, it will change the centroids and it will see how many similar points are there around that center. This is the basic, behind the scenes of K-means. Now we'll go to the hands-on session. So these points anyway you all know. So first one I imported that, and here I have taken the data set of mall customers. So in that mall customers only I'm concentrating only on the third and fourth. So on that annual income and how much they are spending. So only I need only that two columns only. The remaining are unnecessary for me. So what I'm doing, I'm first loading the data. Just loading the data. Here I'm seeing that first five, and then this is about the pre-processing. The third step we have discussed. Just seeing the pre-processing. So info means here I'm seeing whether any null object is there or not. No, nothing is there. I have 200 entities. I have 200 rows. And in that nothing, no null value is there, so I can go. So now I'm going to split that data, and here only I'm concentrating of 3 and 4 column only. So salary, income, and annual spending. That only I'm taking. The remaining I'm just dropping. I'm neglecting the other remaining columns. And here from sklearn dot cluster, because it's a cluster algorithm. So from the cluster module, we are importing the k-means. K-means we are going to do. So we are importing the k-means. Here, this is the clustering set. First initial basic clustering set. We don't know anything. Centroid clustering set. We are just making it as an empty set because randomly we will select a centroid first. We don't know where we have to select and what points it will go in case a cluster. So we don't know nothing. So randomly we will select a basic centroid. So that's what it means. It is first randomly it is initialized to 0 null value, and then once it is checking each and every data point, so if the similarity is there, then it will add to that particular cluster. So this is the meaning of this. And the random state 40 already I have explained. So up to 40, the same answers will be repeated. And then once it is fitted to everything, once the centroids are fixed and some clusters are happened, then we are asking the k-means to fit the line, fit the logic. Here actually, yesterday I told you this thing I should do before the fitting, because here the two columns are completely different values. So I just want to make it as a same scalar. So I have used this as standard scalar value. So this thing actually it has to come before here. Here I have to scale it, and then I have to initialize the WCSS set, clustering set, and then I have to fit the line. The plotting here, just plotting that here after doing so many iterations, once after checking the iteration, so these yellow color points are the centroids we got. So each and every centroid, the same color, you can see the same color points are clustered around that centroid. So there is no other, these points are called outliers. So these are completely away from our data set. So these 3 points and these 3 points are called outliers because that are not any participating in our data set. So these are the outliers, and this is how we do a k-means clustering, just based on the centroids. Nothing more, and no difficulty in this. Only centroids. We will calculate the centroid. Depend using the Euclidean distance. This is what K means clustering. Now we move on to another clustering algorithm. So one more basic clustering algorithm is hierarchical clustering. In the same clustering, K-means is the basic clustering, and second clustering algorithm is hierarchical clustering. So hierarchical clustering actually it works like if you want to see the relationship between one variable and another variable, and you want to see the relation between how much the one variable is affecting the output, or how much similarity is there between one feature and suppose I have four features. Suppose I have four features and I want to see how much similarity is there between first feature and third feature. Similarly, second feature and fourth feature. And how much effect is there of these four features on that outcome. So all these things you want to make it like a hierarchy, like a tree structure. So for that we'll use this hierarchical clustering. So just want to give the relation between the features and also a output. So this diagram is called a dendrogram. A dendrogram. Dendrogram will give you the relation between the features. So these short lines will be given for if here at 1 and 3 are given a short lines means those two are more similar. Suppose suppose here I have some four just let us say four genes I have. So this is my gene 1 and this is my gene 2, gene 3, gene 4. So here these genes are colored like something it is red, blue, and white. And second gene is colored like some yellow, and some brown. And third one also light red, light blue, and some light white, some gray color. Like that, genes are divided. Now, if you want to see the similarities, you can directly see the first gene and third genes are somewhat similar compared to the second and fourth. Because here red, blue, and white is there, here light red, light blue, and gray color is there. Somewhat the pixel values are almost same. So we can make it these two as a cluster. As a cluster. So that's what happened here. So if the two things are two features are more similar, then that two will be clustered and it will be denoted with short lines. And if the similarity is little bit, not completely matched. Suppose here for my fourth line, this is blue, and this is somewhat red, and this is somewhat some light brown. So here completely matched is only this blue. Second and fourth, in the second and fourth, only completely matched is only these two. These two or this is not matching, and this is not completely, a little bit only it's a matching. So there is a similarity, but not completely high. That cases will create a little bigger line for to represent that relation between two features. So this structure is called a dendrogram, and next thing is what is the main purpose of hierarchical clustering? So hierarchical clustering is there is no assumption for the clusters like K means we have to assume that some data points are as a group and we have to create a centroid. We have to calculate the distance and we have to create some centroid. But here there is no assumption like that. We just see that points, if there is a similarity, just add that to. If there is a bigger similarity, you just add completely. Or a some smaller similarity as there, with whatever similarity, you just add that. That's it. No assumption. So that is very easy and that is the strength of hierarchical clustering actually. And This actually this hierarchical clustering mainly used in medical sciences to represent different types of hierarchies. They have to represent. Suppose if you are taking a cancer disease, there are so many unrelated different types of cancers are there, and each and every cancer will have a similarity with the other cancer. Maybe you want to give the relation between different types, different features. There, mostly in biological and medical field, we are going to use this hierarchy. And there are mainly two types of hierarchical clustering. So one is agglomerative clustering and divisive clustering. So in simple words, we can call it as a upward clustering and downward clustering. So agglomerative clustering, what happens? Just like my previous example, if one gene is mingling with similar with the third gene, then that two will be added. Then second and fourth will be added. Then is one, three, and two, four. So cluster one and cluster two will be added. So from a single part, at the last of the algorithm, we'll get a complete cluster. So up to down. And here in divisive, first we'll assume that complete data set is a cluster. We won't assume that is a different points. In the agglomerative clustering, we'll assume that is a different data points and we'll see the similarities. We'll add one by one. And but divisive, first starting itself, we assume that that is a complete cluster. From that, now we'll see if data point 1 and 2 are completely different, then we'll divide that. So this is cluster 1, cluster 2. So at the end of the time, from a total cluster 2, we'll get so many clusters. So from top to bottom, this is bottom to top, up down and down to up. So that is the difference between these two. Here we assume that is a complete cluster. Then we will divide depending on the similarity. So mostly we use most of the times we use agglomerative clustering because it is very simple to understand compared to this one. Adding is very easy. When you want to divide, that will be a bit difficult while comparing the similarities. So this will be very easy compared to this one, and this is the most useful, efficient also compared to this. So complexity of hierarchical clustering. Distance matrix is used for deciding which clusters are merged and split, at least quadratic in the number of data points. So merge it, if you want to merge something, first you have to see the similarity, how much similarity you have, how much dependency on each feature on the other, that you have to see. So depending on that only, we can cluster each and every point. How we can implement this in our Google Colab. So here the same R customers I am taking. I'll upload that R customers data. So the basic steps I'm including here, first importing the libraries, and because here I'm going to draw a dendrium, so for that I'm downloading the pyplot, pyplot. It's a bit slow, just wait for once it is uploaded, so I can run that program and show it to you. Let me explain the code in the meantime. So first, just importing the libraries. All customers is loaded. Now I'll run it. So first I have imported the libraries, then the data set is imported, and in this data set only I'm concentrating on third and fourth values. And then here that the in K-means we have downloaded sklearn.cluster. From that particular cluster module, we have downloaded the K-means function. But here we are downloading the hierarchy clustering actually happens in SkyPy library. This is one more library. Skykit library is contained sklearn all that functions. Skykit, that is one library we mainly use for all our algorithms. And this is one more library in Python, SkyPy. So these also consist of few functions, few modules we have. So from SkyPy, I'm downloading cluster of hierarchy. Hierarchy, instead of giving the complete name, I'm just giving SCH. So a shortcut name I'm giving as SCH. And here SCH, this linkage why I am giving means dendron I have to connect, so that will be structured like a tree from your root node, from the children node and grandchildren node. Like that, I have to specify. So there, I have to link from one node to another node. So for that, I am using a linkage method. And what is my matrix type? So in which matrix type I am taking? So every string value will be converted into numerator. That will be converted as a vector. So that which matrix, what type of matrix, what type of operations I am doing on that matrix, that will be done by a word matrix. And here these things are just for the plotting. I am giving the labels. What is my X label, what is my Y label, and what is the typing. And so SQL cluster, now I'm going to use only agglomerative clusters, not using defensive. You can use defensive clustering also here. And here I'm taking my first clusters are 5. So my first clusters I'm taking as 5. So in that 5, first I'm going to, add or, I'm taking that 5 clusters is my basic one. If anything is there while training period, we can increase that. And I'm giving here the color, different color for different clusters. So this is the mall customers. Depending on a particular salary, depending on a particular salary income of the customer, you can see the last here. The last a similar clusters are there. These are very much similar to each and every customer. So that's why we have given very small dendrons here, and then it will be increased depending on the similarity. So the final one is the final cluster is this one. So means after completing the very much similarity of these, this is very small, so this is completely same. Both the values are completely same. So I have given like this. Different colors I have used for depending on the clustering. And this is what hierarchical clustering. A plot, normal plot, scatter plot, you want to see the same thing. Instead of seeing the dendron, you want to see that as a scatter plot. You can type like this. So this is the customers of the clusters of the customers, and of course spending score and annual income. So these are different types of customers, and these are the uh, clusters. So from the previous same mark customers, we have used k-means. There you can see the centroids. So k-means completely worked on the centroid, but here it is not taking any centroid. And here also the same outliers, the same prediction is given from both of the things. The thing is, this mostly used in medical field, not other things. That actually k-means is the basic algorithmic cluster. Hope you understood this one. So we'll move on to the next thing. So these are the basic clustering algorithms of unsupervised learning. So in the supervised learning, we have seen linear regression, logistic regression, and of course KNN, naive Bayes. And a few people are asking about a few more examples for naive Bayes practical session. So if possible, I'll try to give you tomorrow in the question and answer sessions. I'll try to share you that a few more naive Bayes algorithms. And for today's sessions, these four are we have covered from supervised learning. Of course, SVM is there, the most important algorithm. that we'll try to cover today, or if possible, and tomorrow I'll share you that link also. Support vector mesh. That is very important in supervised learning. So in unsupervised learning, we have covered k-means and hierarchy. Those two are the basic algorithms of unsupervised learning. Next, when we will move on to reinforcement learning. Actually, these things should be covered in the yesterday. Actually, so reinforcement learning. So you have now you have an idea of what is supervised learning and unsupervised learning. You see that too. In both of the things, we are giving some features, some inputs we are giving, and depending on that inputs, if it is a labeled data, we are calling that as supervised learning. If it is not a labeled data, then we are calling it as unsupervised learning. But in reinforcement learning, we are not going to give any features, any inputs we are not going to give, any outputs we are not going to give. Just you'll create some environment, like just like this room. You create some environment and you leave a robot there. Reinforcement learning works on some environment and agent concept, reward and punishment concept. Means just like our video games. Video games, the best example is a free fire. So in the free fire, you won't see any inputs and outputs there. Just start, one agent will come, maybe you, agent will come. So you start firing. If you fire correctly, if you kill that opposite enemy, you will get a reward. If you are not able to kill that enemy, you will get a punishment that you yourself will be killed. So that is how a reinforcement algorithm works. That actually that game is built on reinforcement learning. All video games, all the smartphone games will be built on reinforcement learning. So there won't be any inputs and outputs. Just works on based on rewards and punishment. If the machine will understand, and if the machine predicts correctly, then it will get a reward. If it is not able to predict correctly, then it will get a punishment. From it, if it gets a punishment or reward, we call it as a positive reward and negative reward. So if it is getting a positive reward from the feedback, so everywhere feedback will be there in the reinforcement learning. So from the feedback, we can say that so you got a reward, so you can move on to the next level. Then if it is getting a punishment, negative feedback, then we can say you are getting a negative feedback, then you have to improve yourself. The training period should be more, and you have to work again on that particular place. Like that reinforcement learning works. But why we have to go for a reinforcement learning? The thing is, already we have supervised and unsupervised, but why should we have to go for a reinforcement learning? So in real time, actually, in most of the times, we won't get the complete data. Or if, suppose if we get data also, that is not enough for to do some algorithm. So maybe you are doing some healthcare project. Maybe from the hospitals, mostly you won't get the complete data. Some data you'll get, but that is not enough to do any algorithm of unsupervised or supervised. So there you have to build your own features. The machine has to able to learn by itself. What should be the important feature? What feature I have to take? What how I have to move? I have to take the action. I have to predict the output. So like that machine has to learn. So that's for that purpose reinforcement learning comes into the picture. There won't be any inputs and outputs. And this is completely close to human learning. How we learn from the experiences, it also learn from the experiences, just like a robot, a cleaning robot, how it will move in your room. So it will learn from that. If any obstruction comes, it will move to sideways. So like that, it will learn from the experiences, it will learn from the mistakes, and it will move on to the next level. And algorithm learns a policy of how to act in a given environment. So environment is nothing but the condition where it is working, the machine is working. Some prerequisites we will give to the machine. So this is the environment, these are the conditions of the environment. We will give some rules to the machine. We are not giving any features, we will just give some rules. So if you move forward, you can reach that thing. If you are moving backward, you will know there will be some obstruction. Like that will give some rules. So it will have it has some policy of whether if I move forward, I'll get a reward. If I move backward, I'll get a negative reward. Like that, some policies will be given to for the environment, for the agent. And every action has some impact in the environment, and the environment provides rewards the guides that guides the learning algorithm. Whenever it is correctly predicting, it is giving the um, reward. So, meaning of reinforcement. Occurrence of an event in a proper relation to be a response that tends to increase the probability that the response will occur again. So, if it gets reward, so reinforcement means the implementation. So again and again, once you get the reward, it has to implement it again and again. So once you are getting reward means once the agent is getting reward means it is going in the correct way. So it has to implement that and it has to continue that reward policy. From that reinforcement learning name has taken. And reinforcement learning is a problem faced by an agent that learns behavior through trial and error interactions with the dynamic environment. And here we have a few types of reinforcement learning, actually few learning that we'll see. And reinforcement learning is not a type of neural network, nor it is an alternative to neural networks. So neural networks is a thing of our brain. It resembles like our brain, how our brain works. The neural networks are completely a mimic of our brain networks. But reinforcement learning is not like a neural network. It's just like a LIC agent. How a person will get if more LIC is covered, then he will get a reward. If not, monthly salary will be deducted. It's just like that. It's not like neural networks. Most of the people are confusing like reinforcement learning is completely neural networks. No, deep learning is completely neural network, but not the reinforcement learning. So this is the basic structure of reinforcement learning. So we have an agent, we have an environment. Whenever that reward comes, first it will in the state. Every time it will be a one state, and it will take the action, and the state will be changed. And then by changing the state, it will get whether reward or negative feedback. So this is the structure of reinforcement learning. So this new learning in today or mostly tomorrow we will do that work on. And next today's topic will go. So today's topic is completely optimizing techniques. So in the starting class, I told you machine learning while explaining the machine learning basics. I have explained you machine learning has so many advantages. You know, compared to this normal traditional programming, it's like it's so many advantages are there, but still machine learning suffers with a lot of issues. The main issue I have already told you underfitting and overfitting and bias and variance. So I hope you remember underfitting and overfitting. So whenever the data is not enough, insufficient for the machine to understand the underlying features of the data, underlying relations between the feature and output, then that is called underfitting data. The data is not sufficient to understand, to analyze, to build the model. When the data is insufficient, then we call it as an underfitting. So when a data is underfitting, what will happen? Suppose I have a graph of suppose here I am doing a project of my weight and height, a person weight and height. Weight and height. So when I plot the statistically, suppose let's say this is some weight is like this and heights here like this. So when I plot statistically, I can plot the graph like this. So this is my graph. So mission will work on mission also will work. Which one is better fit line that already I explained you in linear regression. So it is fitted some line somewhat here. Just to say somewhat here. Now I want to predict the weight of some person 75 kg. So want to predict a particular person of 75 kg, the height I want to predict. So from the graph, I can easily say this is my the person height. So this is my y actual. From the graph, from the statistical method, I can easily say this is my y actual. But machine decided that this is after training so many times, depending on whatever algorithm we have given, it is decided that this is the best fit line. Best fit line. So according to this, the height is this one. So this is y predicted. That's a y bar. Now there is a difference. In the training period only I am talking, not the testing period. In the training period only I am talking. In the training period only, this has to train actually up to this only. The line should be like this. If the training is correct, that line should be like this, somewhat like this. But the machine has not trained enough because the data is not enough. So it has confirmed this is the best line. So there is a difference between these two. This difference, this error, we call it as bias. So bias always occurs when the data is underfitting. Underfitting and in the particular training. In the particular training, there are difference between the actual training curve and the predicted training curve. The difference is called bias. When it is a overfitting data, suppose you have given so much data to the machine. So already I told you that is a overfitting problem. So again, this is weight and height. And I'm giving so much data. So now machine learned so much of features. So it built some complex curve, not like a linear curve. It has built some complex curve because it learned so many things, so much. Now I want to predict the same 75 kg of weight. So my testing curve actually from the statistical method, I know that this is my testing curve. This is actual curve of testing. But this is a complex curve. Yeah, it is complex curve. How much you train that, it cannot generalize to this point. Never this point will come on this. This curve never touch this point. Never it can able to predict this point. So this difference, there is a difference now. So this difference is called variance. So variance always occur in the overfitting and in testing period. Whenever the machine is not able to generalize to a new inputs, then that is called a variance. So bias and variance are the main problems of machine learning. So if any algorithm you take, first your basic thing is to reduce the variance. When the variance is not reduced, if it is a high variance, then what will happen? Your machine model will not be, maybe the training period is very good. It has training, very good. Here the bias is almost zero. Trains very well. But when you give a new input, it is not able to predict that output. So when it is not able to predict the new input, our model is a complete waste. So whenever you do a machine learning algorithm, you have to reduce the variance. Always it should be a low variance. So the machine model should be generalized to new inputs. Now we'll see this basic, bias and variance concept using linear regression and polynomial regression. That two things we'll see on hands-on, and how the bias and variance concept will occur, that we'll see. Just opening one more. So these links will be shared to you. First, K-means link already yesterday we have shared in the WhatsApp, and previous one hierarchical link and the mall customers data also yesterday we have shared. Hierarchical clustering link will be shared to you now, and of course this bias and variance also shared to you now. Okay, now we'll see this one. So uh, here two things I am going to consider for to make a difference between bias and variance. How it can happen? How in what is a high bias? What is a high variance? To represent that, I will take. So to make it clear, these two I am considering. So I'm considering two regression algorithms. One is a linear regression. So I'm considering a polynomial equation here, which is having a quadratic equation of power 2. So here I'm considering that an equation, just an equation, and I want to see how the machine will fit few values on that equation. And for this, I'm considering a linear regression. I'm just first assume that all the points have a linear relationship between these two variables. I'm considering an independent and dependent variable. I'm just assuming that both have a linear relationship at the starting. And of course, second time I'll assume that there is no linear relationship. There is a polynomial relationship. So that's why I'm considering two regression algorithms. One is linear regression and one is polynomial regression. Both the things I'm going to use here. And mean squared error is to calculate the bias, how much bias MSC we'll call it as. So MSC is called to identify how much error we are getting it, from that training, actual training curve and predicted training curve, how much error we are getting. That will decide in the terms of either the mean squared error or MAE, mean absolute error. So different metrics are there. So mean squared error, mean absolute error, all these things. So here just considering mean square error. So I will square all that complete errors, different errors, each and every point, and I'll take the mean of that error. That is nothing but MSC. So one value will get at the end. And now we will share bias and variance link and hierarchical clustering link. Both the links we have shared in our WhatsApp channel. Please check it and open the bias and variance Google for that project. And next one, here I'm taking the speed as 42. It's nothing but a random state. Instead of state, I am taking as seed. Seed is nothing but 42 times the randomness will be same. So it will not be changed at the 43rd time, it will be changed. And here that line space why I am considering is this one. So 100 points I am taking. I'm considering a quadratic equation first. So 100 points I am considering. I'm assuming that 100 points are equally spaced, and in each space it is only 10 points. So equally spaced, like it's just a matrix means it is spaced in like 10, 10, 10, 10 points and total of 100 points. And the shape of that matrix is -1 and 1. So means that one column I have and 100 rows I have. There is no column. One column only I have. 100 rows I have. That is my shape. So one-dimensional matrix. So that is the meaning of this line. And this is the equation. Equation what I am going to consider sample equation. Now I'm just plotting the data. I want to see how it will be plotted. So this is plotting of title, X label, Y label. Now here first I'll fit my whatever points I have considered. I'll fit with linear regression. So already you have learned how to fit with a linear regression. So just I'll fit with my X and Y. X is some rows and my Y is the one more in the quadratic equation I have X square plus some Y plus some constant. So that values I am plotting. So that values here I am considering as input and output, and that I am going to fit with linear regression first. And then next I am considering this polynomial equation. So for the polynomial equation, here I am considering the maximum power should be 4. The maximum power, actually it is I'm considering only two. But the maximum level I'm considering and taking for safety purpose, I'm taking as 4. Poly degree I'm taking as 4. Now I'll fit that x and y using polynomial fit transform. So both the things I have fitted and I have trained that values in both the things. Then we'll see the result. Now the next things are just plotting. A scatter plot I want and a PLT plot I want with a color red. So blue colors are completely the actual data, actual training data or actual testing data. Whenever you are getting a red line, that is completely predicted data, predicted by machine. These my points from 1 to 100 values I have considered. So these are the values. And this is the linear regression. It's a relation is built like a linear regression, and this is polynomial regression. If you run the graph, you can analyze that linear regression has covered only few points. It covers only few points. It is left behind of so many points here in this part. But polynomial equation is very flexible with the data points. So so normally from the equation you can see that that is a quadratic equation. Definitely it is not a linear regression. So when you see that bias and variance, so here MSC, the error between those two are when linear regression it is 440. 440 means in the training period it is getting very high bias. Bias only I'm calculating bias, very high bias. But in case of polynomial regression, this is 171. Means that in the training period, the model are when it is using a polynomial regression, the model is able to understand the inline features. So the training curve is not that much distance from the actual curve. So there is a less distance. So the error is automatically reduced. So we can call this is a high biasing linear regression and this is a very low biasing polynomial regression. So this is how we will calculate the bias. Now we will share the quiz of today. This is the link of today, and then after coming back from the quiz, we will see how a PCA will work. The remaining optimization techniques, PCA and gradient descent, how it will work, and how the hands-on sessions will be. We have to do that PCA and the gradient techniques. So now the link will be shared to you. Please go through the link. Already we have learned all the concepts in the previous classes. Welcome back and hope everyone attended this program session. And somebody asked me to explain the bias and variance to you again. Just in 2 minutes, I'll cover things and then we'll move to the next topic. And so bias and variance, I hope we understood the difference between bias and variance. Bias is actually occurred when in the training period and the data is insufficient to learn the relation between input and output. And variance will occur in the testing period when the data is too much efficient and it has learned so much. It has built the complexity. So that is what bias and variance. So here to make the difference between bias and variance for this experiment, I have considered simple quadratic equations like 2x square plus 3x plus 5. So I have considered some quadratic equation and I have added some noise here because in real time, whatever data you have created, it won't be completely clean there. Only there will be some noise. So just so I have added a few noise for that. Definitely, if the noise is there, then only we will get some difference between the training and the testing. What is the difference that we can able to understand. So I have considered the quadratic equation here. And to make a difference between bias and variance, I have considered I am going to apply two algorithms in this session. One is linear regression and one is polynomial regression. So linear regression always assumes that the relation between the independent variable and dependent variable is always a linear. linear relationship y equal to mx plus c. Polynomial relation, the polynomial regression is it's not linear. It won't accept that the relation is a linear. So it will be some curve like that. That is the only difference between the archetype. So this is a linear relationship. This is a some non-linear relationship. So I have first imported whatever libraries I want. So I want linear regression and I want polynomial regression. Both I have downloaded, I have imported. And to calculate the error, directly we cannot calculate error in machine learning. Either that error, for each and every point, some error will be there. So each and every point, we cannot show what is the error value. Some integer value we cannot show. So what we'll do, we have to gather up all the, aggregate all the errors, and some more we have to use. Some method we have to use for aggregating. So for that, I have here the metrics will be like mean squared error one metric will be there, and mean absolute error, mean absolute squared error is there. So many methods are there to calculate that particular error in particular points, each and every point. So here in that I have considered mean squared error, MSE, that is called MSE. So MSE I have considered. So depending on this MSE value, I will decide whether the bias is higher or lower. And so here this NP dot seed is nothing but the fast, how much fast I want. So up to 42 iterations. Here I have given 42. It's just like same like whatever we have learned random underscore state. So the randomness will be up to 42 iterations. It will be very fast and it will be safe. It will be consistent with the results. And 43rd time, maybe the speed will be changed and the randomness will be different from 40 to 42. And next thing is just plotting the data. Next one is that I have plotted the data. And here the two things are, first thing I am going to fit the line using the linear regression. So linear regression. And second, I am going to fit the line. And it means I am finding the data in polynomial regression. So in the polynomial regression, it's a quadratic equation, power of 2, but here the maximum degree I am assuming while doing the operations, I am assuming the maximum degree is 4. You can make it as 2 or 3. But I am assuming for my safety purpose, I am assuming 4. That's it. And here I have fitted the line using polynomial regression. Now, this is completely about the visualization part. What should be my label and what color here, the color I want for my actual data is green and polynomial level predicted data to be in the red. Like that, I have given the colors, the plotting position. And if you run this and if you see the mean squared error, is the curve we got, and here the mean square error for the linear regression is the more compared to polynomial regression. Here the mean square error is 440 and polynomial regression is 171. Means that polynomial regression understood better compared to linear regression. It understood better the data. Underlying features will be understood better by polynomial regression. Why? Because it is not decided that the relation is a linear relation between the two variables. So it understood better compared to linear regression. So the error is reduced. Means the training curve is almost near to our actual training curve. The error is almost less. This is what the bias and variance. Variance also same thing. When you here instead of your training, if you try it with X test, then you'll get the variance for linear regression and polynomial regression. The next thing we will go for PCA. One more important concept of PCA. So PCA means that principal component analysis. So why we need to go for a PCA first? I'll start this thing with an example. Suppose I have a student data. Suppose I have a 5 students data of a particular student is very good in maths and a particular student is very good in English. So I have a data of a student names, student one, student two, like that names, and also math score and English score. So how many dimensions I have? Two features I have. Now, how I'll plot? Well, so some example I'll take. So let's say the same weight and height concept we'll take. So I have a data of some mice, I have. So I have a data of suppose the mice weight and mice one I have. So this is the mice weight and mice height. One mice height and weight. So how I'll plot this? This is the weight of only for one mice. So I can plot directly. I can plot directly on a single line because it is just only one data. Now, for example, I am increasing the features instead of, first I'll take only weight. So I'll plot all the weights here. If I am increasing the features here, one more, one more, one more, one more. So what I will do? The feature is increasing. I want to plot both the things. If weight and height are there. So I want to plot weight and height and 2D. Suppose I'm increasing one more feature and one more direction. So I'll include some z direction or some negative z, positive z or negative z. Then I'll include that feature also. If suppose I'm increasing the features, still I'm increasing the features. So how I'll represent. So feature is dimensionality is nothing but how many features you have to plot all these things in real time. So all these things are a graph. But if there is 100 features, so how much the dimensionality? It's 100. That for manually, it is impossible to draw that. That type of cases to reduce the dimensionality, I will use a concept of principal component analysis. Principal component analysis mainly used to reduce the dimensionality and also uh, by reducing the dimensionality, it has to give a complete explanation of the features. We cannot neglect all the features. If 100 features are there, maybe 70 features are useful for me to plot the graph, to build a model. So 70 dimensionals I have to use. But 70 dimensions, I cannot see that 70 dimensions. So I want to plot that complete 70 dimensions in some, one or two dimensions. So I want to reduce the dimensionality. So that for to do that, we will use PCV. PCV is mainly used to reduce the dimensionality. So how we will reduce? For example, the same example I'll take. Suppose I want to, I have plotted the graph like some student maths and here the math score of student and the English score I have plotted here. So whenever the maths score is high, the person also getting a better English score. In some cases, the math score is very low, but the no very low, and the English score is very high. Like that, the plots are there, somewhat like this. If if that is the thing, and I am adding now science also. Some science score also I'm adding, and my project is to decide whether the student will get a placement or not, or whether the student will get a better college for higher studies or not. So how I will do? If I see like this from a direct view, I cannot able to see all the features if the dimensionality is increasing one by one. I cannot see all the features. So what I will do? I'll just PCA is in simple words. What is that? It will just tilt that angle. And if I cannot see from the front view, I'll just tilt that the complete environment a little bit. So instead of seeing like this, I'll tilt that. So I can see better view of all the features. And here it's a 2D picture, I cannot see. So I'll just tilt that. It's a 3D picture. So I can see each and every feature. So if I can able to tilt and if I can form a line after tilting by touching all the features, then that is called a principal component. So like that, how many ways you can tilt and how many different principal component lines you can form, that you have to decide depending on your application. For example, suppose these are my points. Let's say these are my points. I just tilted this line. So let's say some 45 degrees from angle I have tilted. Now all the points I can see. This down, some depth points also I can see. And I am now fitting the line with all the points. Now I'll call this as principal component line of 1. Now here are also few features I cannot able to see. Now again I am tilt this environment a few more. And now it's still now I can see few more features. Then again I'm fitting the line there. So that I can call it as PC2. Principal component line 1, principal component line 2. So like that, depending on your application, how many principal component lines you can fix, that you have to decide. So principal component analysis mainly use it to reduce the dimensions. That is the first factor. Second one is it will be used to decide what is the effect of each feature on another feature. Suppose in medical field, actually when you are working on a drug detection, on the drug, so which drug will contain the particular ingredients, and depending on that ingredients, you have to make a perfect drug. And machine learning algorithm will predict the correct ingredients of the particular drug. So there you have to know what is the influence of each ingredient on the drug, and also what is the effect of what is the percentage of effect of that particular ingredient when you use in drug. Because in some drugs only we have to add only 50% of a particular ingredients. We cannot add more of that. Some ingredients will be added some 80%. In that case, to divide that percentage of ingredients, you have you can use this principal component analysis for better efficiency. So principal component analysis is first to determine the dimensionality, I mean reduce the dimensionality, and second is to decide the dependency of, or to decide the effect of features on the variables, I mean outputs. And also it will decide the percentage of effect of each feature on the variable. That is the third point. And fourth point is it will show what is the effect of each and every variable in between. I mean, what is the relation between each and every variable? So if you are adding 3 ingredients in a drug, so what is the effect of each ingredient on other ingredient? So in between feature and feature, what is the relation between features also, it will be, we can know from the PCA. So in machine learning, we normally work on heat maps to know the relation between features. So to know the relations between features, we will draw a heat map. That anyway we'll see in deep learning, heat maps. So to read the heat maps or to efficiently present the heat maps, we require the PCA. There are many users using the PCA. So we have to, this is the basic concept, an important concept in PCA. And so PCA mainly, the main concepts of PCA are, first one is variance. So variance is nothing but how the data points are correlated to each other. Or suppose I have a 5 data points. Suppose I have 5 data points, and variance is nothing but how a data point is completely distracted from the mean. How much distance it has from the mean. So suppose I have 5 points, so I can easily calculate the mean. So the mean value will be there. So each and every point I will calculate how much it is distracted from the mean, how much distance it is having from the mean. So that particular the difference is called a variance. So variance will show you whether the feature is very near to other feature, whether the feature is belong to this or it is a outlier, and how much distance it is there from that particular group. All these things will be decided by variance. And second one is covariance. Covariance is nothing but the direction of that features. Suppose some features are like when one feature is increasing, other feature also will increase. Just like age and salary, when age is increasing, of course salary will increase. So one feature is increasing, another feature is also increases. Then we can call it as a positive covariance. In some cases, when one feature is increasing, the other feature will reduce. Suppose like height and weight. At some point of a particular limit of weight, the height will not increase. It will no, it will not reduce, but it will make it as the same. In some cases, like whenever something is increasing, demand and sales, demand and supply. In some cases, that type we can take it as an example. So when one feature is increasing, one is in the reverse direction, it will decrease. Then we call it as a negative covariance. So covariance is particularly about the direction. So variance is particularly about the value, how much distance it is there from the mean. And covariance is particularly about the direction, in what direction that features are going, whether both are going in same way or both are going in different ways. Beside that, we'll study covariance and eigenvalues and eigenvectors. So eigenvalues are like in matrix covariance values. Suppose two features are going in reverse direction. So eigenvalues will give you how much distance they are going, how much fast they are going away from each other, how much, how much effect they have on both of them in going in opposite directions. That is values. Eigenvectors is in how much direction difference is there. So the complete direction it will tell eigenvectors. So eigenvalues and eigenvectors. The last one is dimensionality reduction. So principal component analysis, as I said, first the main concept of PCA is to reduce the dimensionality. So instead of having some 70 dimensions, we just tilt that environment, tilt that platform, and we are making all the points to come into a complete fitted line. That line we'll call it as a PC1. And like that, we'll kill some more and PC2. So instead of having so many 70 dimensions, we have one or two dimensions. Reduce the dimension. These are the main concepts of PCA. Now, how we'll use that PCA? So first one is standardize the data. So as I said in dimensionality, so first thing in PCA, first step in PCA is you have to standardize the data, because each feature will have in some range. Maybe age will have in some range and salaries will have in some range, and each point will have in different ranges. So to apply PCA, because we are tilting the complete platform, if it is in different areas, we are not able to plot the things. So what we'll do is we'll apply these statistical methods like a mean, mode, median, and using these three, we will apply these concepts to each and every row. So each row will be alternated by the mean of that value. So now all the features will be in the same standardized factors, standardized values. So that is the meaning of standardization of data. So each and every value will apply the mean. So if I have a column 1, complete column 1, I'll take the mean, and each value I'll apply that mean value. So like that, I'll apply some standardized for everything. Either I apply mean or base for completing, I'll apply mode or median. That depends on your application. And the second one is compute the covariance matrix. So first we have to know whether the features are completely in the same direction or both are completely in reverse direction. Then depending on that only we have to plot PC1 or PC2, whether both are in complete reverse direction. If you are tilting in a positive way, then almost this another whatever is going in opposite direction, that feature we cannot see. So we have to know first how in which direction it is going. So covariance matrix we have to form first. So directions we have to now compute the eigenvalues and eigenvectors. And as I said, the particular value in the particular direction we have to make it as a matrix. And then sort eigenvalues and eigenvector and select the principal components. So once the matrix, the values, the mean, standardized, everything is over, then you place the PC1. Where that line you can place after clicking.
Yeah.
And what are the applications of PC? So
Mm.
first application is data visualization. So to visualize better, because 70, if it is a 70 dimensional data, so it's very difficult actually practically we cannot see the 70 dimensional. In we whatever may be the algorithm, you cannot able to see that 70 dimensions. In real time, that will be more and more dimensions. So to better visualization, we will reduce the dimensions and instead of having a some 50 dimensions, we'll make it as some 4 or 5 dimensions. So visualization will be better, plotting will be better, understanding will be better. That is the first application of PC. Second one is noise reduction. So if we are having some 50 dimensions, 50 dimensions means 50 features you have. When you are going for actually PCM, it really useful in neural networks because neural networks, each and every feature we have to create a layers. So different layers, and in that particular layers we have to create the nodes. So suppose I have a 50 features. So 50 features layers I have to create. So in that, maybe some features are useless for me, but I have to create that layer as well. I have to see whether the feature is important or not. Before calculating the covariance, I don't know whether the feature is important for me or not. So instead of creating that and filtering, we can see that whether the feature is fitting for our line or not. If it is not fitting anywhere, then we can say that the feature is useless. We can remove that feature. So automatically dimensionality will reduce. So remove the noise. Whatever is not applicable for our application or for our product, we can remove that things. So that is what reducing the noise. And third one is feature extraction. So feature extraction is nothing but which feature is important. Suppose I have 50 features. Suppose I am doing a student campus placement data project. So for that, I don't need actually address of the student feature. That feature is important, unimportant for me. So I can remove that feature. So better feature extractions, what are the better feature extractions that we can look at? What are the better features for our application? That will be decided by PCA. Now, everywhere we are using the variance. So variance will give you the relationship between each and every feature. How a point is away from its mean. So it will give you the distance each and every time. So depending on that value, we can say whether this particular feature is influencing the output or not. So feature extraction is better if we use this. And pre-processing for other algorithms. So better pre-processing if the dimensionality is reduced. It is easy to understand the data. It is easy to analyze the data. It is easy to see whether there is duplication of the data. This is what about this. Let's see how we can implement this in our Google Colab. So we will share the PCA link. Already we have shared the PCA link to you. So open that. We already shared you the PCA link. It's my so here I have downloaded. I have imported a direct iris data. So last class I have told you an sklearn, and clearn will consist of both the libraries will consist of a default data sets. It is a Pebble data set. And so directly instead of loading to Kaggle or Google, directly I downloaded the iris data set here. And iris dataset, why particularly this dataset I have considered is iris dataset. If you open the dataset, you will see so many features, almost some 100, 180 features you will see. So means 180 dimensionality you have to reduce. So actually I have considered it's a very big number. And here this thing already loading the data. Already I have loaded this data here directly from that loading I have considered. So now I'm just taking that into splitting into input and output. Just telling the machine that this is the input and this is the output. And first step in PCA is to calculate, to standardize the data. So for standardizing, I told you already to use any method of any statistical method, whether that is the mean or mode or median. So use that statistical method. So calculate the mean and standard deviation, and after calculating, just store that complete standardized data in the Excel report standardized. So here I am calculating that's mean and standard deviation. And then now I'm importing the PCA here from sklearn library and sklearn library, and here I'm applying the PCA. I'm fitting the data into a PCA line. Here I'm fitting that PCA line for the my standardized data. So here I'm using Excel standardized data. Now this is about the plotting of visualization techniques. What is my X label, what is my Y table, and what is this? And now here you see this PCA curve. When you fit that line, see here, instead of getting sepal length, so many features will have in iris data. Will have a sepal length, sepal width, petal width. Just open the data set, you can see all these things. Some Wernicke, some few features will see so many features. So instead of that features, we will get only one principal component and one principal component one and principal component two. So whatever are important features, whether that are edge features or whether that is centroid features or that is some inline features or maybe the center features, whatever features are important, that features will be collected and it will be shown by a principal component analysis. So automatically so here it is considered only three features. Three important features are affecting the variable perfectly. So it is considered only three features and it is giving the different features here. So dimensionality is red differential. So here nothing we are doing, no prediction, nothing. First what we are doing is before going into the machine learning algorithm, we want to reduce the features. So that's what we are doing in PC. Hope you understood the concept of PCA. Let's move on to one more thing. Next thing is gradient descent. Gradient descent is actually one more optimization technique. And, normally we use gradient descent for our linear regression algorithms. So linear regression algorithm, as you already you have aware of that, the linear relationship that is maintaining y equal to mx plus c. So it's a linear relationship. But suppose you have a data and you have applied linear regression algorithm and it has given you the best fit line using least square method. So yesterday I told you that the day after before yesterday in our second class I told you least square method, how to calculate the least square method. So it is calculated and given you best fit line. But to while getting that best fit line, so every time the model will change the line. Starting, it will make that line as somewhere. This is my data. Let's say this is X and Y. So this is my data points I have. So suppose that mission assumes this is the best fit line of one. Let's say this is fit line of one. Then it is calculated from each and every point. It is calculated the least square distances, and it is more from the actual data. Then again it is decided this is not fit line. Again while trying it is calculated fit to. But how it is knowing that is the minimum distance? So there should be some method. So that method is called a gradient descent. To reduce the least square distance, to optimize the distance, to minimize the distance between the actual curve and the first fit line, we use that method as gradient descent. So gradient descent will minimize the distance, the error between the actual and predicted line. So yesterday I told you the error, whichever we are getting from the actual curve and predicted curve, we call it as loss. Loss. Loss or cost. Cost function we call it. So cost function is nothing but the difference between the actual curve, actual predicted curve, but and the actual curve and predicted curve. The difference between these two is nothing but a cost function or cost function. So always any machine learning algorithm will try to reduce this error. If that loss or cost function is minimum, then your algorithm will be better. That is increasing, then your model will be, we have to rework on that model. So to reduce this thing, it will be used. Gradient descent is the one technique being used to reduce this loss and cost function. Mainly used to reduce the loss and cost function. So what is a gradient descent curve? So just take an example of, imagine we have a data set of single picture y and target variable y. Suppose and we want to fit a straight line to this data. The goal is to find the best fitting line by minimizing the differences between the predicted values and actual values. So this is actually the cost function or loss function. So here this theta 1 and theta 2 are, this theta 1 and theta 2 are, this is my graph. So let's say this is my fit line. So now linear relationship is y equal to mx plus c. So the intercept is from x-axis. What is my intercept? That this is like my intercept c, and slope is m. Now this theta naught is my intercept value, c value, and theta 1 is my slope value. So loss function always a complete function of the slope and intercept. So when you reduce that this fit function, you have to reduce either intercept or you have to reduce the slope. Those two are irreversible. Then if it is increasing, it should decrease to minimize that. So this is always a cost function is a function of intercept and slope. This is called a cost function and it is given by, this is actual value, h theta of xi is actual value and this yi is predicted value. This yi is predicted value. So each and every point will calculate what is the difference. So we have different points here. We have different points here. So each and every point will calculate, this is our actual curve. So every point will calculate what is the difference. And we will scale the aggregate all that points, will square that, and from 1 to m, suppose let's have a m features. So 1 to m will take each and every point difference and we will square it and then we'll summarize everything. This is a constant to reduce. In some cases, suppose the regression curve is like this. So whatever points I have, it may cancelled by these values because these are positive values and these are negative values. To reduce the collision between the positive and negatives, we are introducing a constant. Some constant that features m is nothing but the features. So this is the cost function, whatever we apply for linear regression algorithms. So our aim is to reduce this one. We have to minimize this one. So how we will minimize this one? So to minimize this one, to minimize any function, some quadratic function or any function f of x. Suppose you want to reduce a f of x, you might have learned in your basic maths like the derivative you have to take of that particular function and equal to 0. Then you will get the minimum value of that function. The same thing will do here also. The gradient descent will take the function, will take the cost values in terms of intercept and slope, and will create that function and will take the derivative of that function and will equate to 0. Then we will get the values of minimum values, uh, and minimum least squared distances we will get everywhere. From that we will plot the best fit line. So how linear regression will work means depending on the gradient descent. Yeah, this is what gradient descent function. So we will just take the derivative of this function and we will we will equate that to 0. So that is what a gradient descent. We'll see how we'll apply this gradient descent in our collab. So this thing also already shared with you. And the gradient descent. So here I have considered uh, some random data I have considered, some 100 features I have considered, whatever maybe some values, input values I have considered of 100 values. Just I'm taking like the size of the matrix should be I should have a one-dimensional array. So 100 rows should be there and only one column. So one-dimensional array. And this speed already I have explained you because up to 42 times the same results will be repeated. The randomness will be same for up to 42 times. And 43rd time it should be different. So like that I consider. And for my project, this project is here nothing no more bigger data I am not studying. Just a linear regression problem I am taking. So for that, I'll just use a numerical analysis. So I imported the NumPy and for the viewing visualizing capacity, and I have imported the match problem. And here again, I have considered a sample, simple equation 4 plus 3x. So y equal to mx plus c. So here my slope is 3 and my intercept is 4. So I have considered y equal to mx plus c. And here for the real time purpose, I'm adding some noise. So that noise, if I add that noise, then only I can see whether my model is working on bias and variance. That for that purpose only I'm adding extra noise. You can do the same problem without noise also. And now, so here this is actually for my intercept 4. Each and every where I'm taking that intercept as a function. For x, I am taking that intercept because to minimize that function, either I have to reduce the intercept or either I have to reduce the slope. So here I have considered of reducing the intercept. So I'll consider that intercept as a function here. And this theta is nothing but a small function I am assuming for a complete thing. This quadratic equation will be in that function, and I am going to derivative that of theta, and then I'll equate that to 0. So that's what we are and doing. Here, cost function, the same formula, whatever we have explained the previous PPT, that same thing I have considered here. So 1 by 2m into this is the actual loss of uh, that actual predictions and the actual data and the predicted data. So this is my loss. So this thing I have to calculate. I have to square it and I have to sum it. So I have used all that numerical calculation. So I have used NP dot sum and NP dot square. And these are the predictions minus actual data minus predictions. So I'm using this and then I have to multiply this. So I have first calculated the cost function when I am taking intercept as a function. Here I'm taking only for 3%. Now this cost history, again calculating after cost history. First I am for the iterations, first I initialize that to 0, and then using a loop, here using a loop, I am creating this, I am creating this theta function, and whatever I am getting here, that the cost values, I am taking that cost values into this function of this variable of theta. So theta is my one more function which I am going to derive and equate to 0. So this is my particular function here. So here learning rate is nothing but uh, actually this is the gradient descent. So my, let's say let's say uh, this is my x and y. So let's say this is my actual curve and this is my predicted curve. So now I want to reduce the difference at each particular point. Now only that errors I am plotting on a graph. So on a graph, when I plot only that differences, so I'll get that graph like this. Let's say I got the graph like this. So I can call it this as cost function graph. Now learning rate is nothing but how we are moving to reduce on this graph and how much fast you are moving. So our aim is to convert this graph to a minimum value. So let's say I'll draw like this, then you'll understand better. So let's say this is my error graph. Whatever error I am getting here from the actual and prediction, this is my actual error graph, cost function graph. So now my aim is to get only the values up to here. Means it is very near to 0, near to 0 axis. So I want all my cost function values here. So that is my final aim. That is what I am doing in gradient descent. My final aim is to reduce this complete cost function values to here. So means converging the complete cost function values to 0. How I will do that? I have to move each and every value and I have to do some operations, some each and every value I have to take. I have to take the derivative and I have to equate 0. But how much fast I am doing that? That is learning rate. So how much fast I am doing? How much fast I am moving from this point to this point, this point to this point. So how much fast I am moving to this end minimum value. This is actually we call it as local minimum. So that fast of that the speed, the graph is learning, the curve is learning, the model is learning. That is called a learning rate. Suppose learning rate is more. For example, if you are just getting down from a hill, so what do you do? Normally at the starting, you will walk fast. When the curve is very steep, then you will reduce your speed and you will go very slowly. But when the curve is a better, like a plane, then you will increase your speed and you will go fast. Same thing happens here. So learning rate will not be same throughout the process. So sometimes we can go fast, sometimes the machine can learn fast, sometimes the machine should learn very slowly. So that depending on that learning rate will change. So if here from here to here, if it learning rate is very slow from the starting, from this point to this point, if the learning rate is very low, so no use of that. It's just waste of time for us. It's waste of computational speed. You can go a very fast here. Better, bigger steps you can take. But when you come to particular this point, you have to make your cost function derivation a very slow, a bit slow, because wherever you will get 0 point, that you don't know, that mission you don't know. By seeing this code as a human, we can tell that this is our 0 point, but missions cannot able to understand. So we have to reduce the learning rate. So once you reach this point, the learning rate should be reduced, and then it has to move very slowly. And at the final, wherever you get the minimum cost function equal to almost zero, then the process will be stopped. This is what happens in gradient descent. That is what I have given here. This is the learning rate I am giving. Learning rate into gradients. Gradients is nothing but these these values of cost functions, the derivative values of cost functions. So I am calculating these, multiplying these values with our learning rate, and I'm taking the difference of our main derivative of that function of intercepts. So this is the meaning of this formula. This is the main formula for our gradient descent. Now, after calculating this gradient descent, now we'll just save that history of that gradient descent, and we'll move on to the plot. The plot, fitting the line. Now, after calculating that thing, we will fit that line with that particular learning rate and with that functions. Whatever we have calculated that functions, we will fit that line. Then we'll just run this thing. Next thing is completely plotting. How we will plot that function and all. This and see, you can see is the cost function. So this is the cost function. So normally cost function, we can see here up to here it is completely steep graph. So the learning rate is very fast, but here when it comes to zero, this is very the learning rate. You can see the scatter plot here. Some blurriness is there. So learning rate is very slow in this particular plot. When it is reached here, this point, the learning rate is very slow. Means the machine is learning very slowly at that particular point. And after that, again, it is a plain area, so the learning rate is very high here. This is the number of iterations, and this is the cost function. This is about gradient descent. Gradient descent mainly used for prediction of the difference between the error between actual and prediction. So these are the basic optimization techniques in machine learning. So tomorrow's class is completely Q&A session. So you practice all these things. If you have any doubts, you can ask me tomorrow. And all the quiz also I'll discuss tomorrow. What are the answers should be there and why where you have made a mistake. And if you want to learn some more concepts, you can chat me. You can give me in the chat box. Of course, reinforcement learning that we will see in the next class. We will share you the feedback link. Thank you and good night.